Hello guys, nice to see you.
Good afternoon.
Hi. How are you doing?
Well,
That's good. Hello.
Hello.
Hi.
good morning.
Hello. Nice to see you. Yeah, I'm doing also okay, thank you. Weekend is coming, it's good. So, I believe most who wanted to join are already here. So, just short recall of our previous discussion. We were working on introducing the three laws of motion and discussing them in details. So probably it's better if I write them down again. Do it here. So first law of motion was when we have some net force applied to a body in inertial system, like a reference frame of reference. Then it should move along straight line with constant velocity or be stationary. So then velocity is equal to 0. So this is the first law of motion. Second is defined as acceleration is equal to the net force divided by the mass, which is inertial mass, not gravitational, but they just equal to each other. So, and the third, if we have some, for example, some system of two bodies, then it is, there is some acting force and there is the same in magnitude but opposite in direction reacting force. So these three laws of motion are important to remember, and now we will consider to apply them in like different consider different applications of laws of motion. So for instance, at the beginning, let us consider an inclined frictionless surface. Friction we will consider shortly after this in details. So if here is some body, we have weight of this body, mg, and it's convenient to consider axis x and y like this, x, y, perpendicular to the surface and along the surface. And now we can consider components of this of this weight, which is and also the reaction of the surface. So here we have angle theta, means that this angle will be the same here, theta. Because it's angle between the inclined plane and horizontal. And here is angle between the normal to this inclined plane and vertical. So they are the same. And if we consider the orientation of like component of mg along axis y, so this will be mg times cosinus theta. And also will be some component along axis x will be mg times sinus theta. And here obviously will be reaction of the surface n. So now we can write for axis y and x our net forces. So y, it will be positive n because it's along axis y minus mg cosinus theta equals to 0. So it doesn't move along axis y. At axis x, we have only one force along axis x, and this is mg times sinus theta, which will result in some acceleration. So we can cancel this mass and get that acceleration is equal to g times sinus theta. So this will be the relationship of acceleration along axis x and angle theta, taking into account g, and this has some practical interest because it's convenient if we consider some frictionless surface. It's convenient to measure gravitational like this acceleration of free fall g as a divided by sinus theta. If we keep sinus theta small, we can measure it, but it's small, then a will be also small, and it's easy and to measure a, like small a acceleration at high accuracy. So such approach could help to get high accuracy of determining the acceleration of free fall. So this is frictionless example. We will come back to this with static friction a little bit later. Second example, it could be some this classical example of a body in a lift. So here we have mg. Let's have here our axis y. And at v constant of this system, like whole system, a lift with the body, or v equal to 0, we don't have any acceleration, of course. Then we have reaction of the surface, and this is they compensate each other. So now let us consider the case when we have some positive acceleration aligned along the axis y. So it's a. So for previous case, when we didn't have any acceleration, we could write as a projection of this vectors, forces vectors on axis y. We could write that positive n minus mg is equal to 0. So that is clear. Now, when we have some, when this lift is moving upwards with some acceleration a, we can, which is like positive, so a is positive. Then we can write m times a is equal to n minus mg. And from here, we can rearrange it in order to express n. It's equal to m times a plus g. So we get the equation for n, and in this case, it is larger than the weight of the body because we have additional acceleration oriented upwards. So obviously, if we have the case with acceleration oriented downwards in the opposite direction to the axis y. Oh, okay, you can ask your question, yeah, Artuna.
Yes, I'm sorry. I just wanted to ask, is there any possibility to show ones that we had previously written? I mean, before this slide.
Of course, yeah. You mean this, yeah?
Yes, just a minute. Okay, thank you.
Yeah, no problems. So now we consider negative A, and this will be minus MA is equal to N minus MG. After rearrangement, we will get that N is equal to M times G minus A. So we see that now the reaction decreases, and if A is equal to G, then N will be equal to 0. So it will experience like free falling condition, the body, with no reaction from the surface on which it resides. So it can be like free body, free falling body. So that's something what is realized, for instance, continuously at International Space Station. It's continuously falling on the Earth, but moves so fast that it doesn't manage to fall. And while it's continuously in the free falling condition, the like objects inside this space station and also like astronauts do not experience any gravity because they continuously stay in this free falling condition. So keep in mind that there is no gravity on effect on International Space Station, not because it's so far from Earth that gravity is so weak. It's actually quite close to Earth, and there will not be a big difference in gravity in free fall or acceleration on the surface of Earth or in the space station. It will be a little bit smaller, but not so much. But the fact that astronauts don't experience gravity, it's just because of free falling condition. Okay, so now we go to another step, which is introducing friction forces, and that is very important because friction has a strong influence on the motion of bodies. So for this purpose, let's consider a body on some surface, horizontal surface. Let's have some mg, the weight of this body. Then it is compensated with reaction of the surface. And now assume that we exert some force on this body, F. And if we have some force which is not compensated in this case, we should expect something like this. So we should expect some acceleration of this body towards right direction, and it will be F applied force divided by M. However, experience tells us that it doesn't happen so easily. You can apply some force to a body, to some box, but it doesn't start to slide immediately. There is some initial like static friction. So it's called static friction force. It is oriented in the opposite direction to apply force. And its maximum value, which is beyond which if force increases, goes higher than this maximum friction value, then body starts to slide, is defined by two parameters. It's actually static friction coefficient, μs, and So it's reaction of the surface. And yeah, but here we don't need vectors because it doesn't define the orientation. So orientation is defined by the applied force to the body, and it will be opposite to the applied force, and the magnitude will be defined by this product of static friction coefficient and reaction of the surface. So static friction coefficient takes into account conditions of the surface, like two surfaces which are in contact. Could be smooth, rough surface, obviously that will be less and more friction between these surfaces. And it's just defined in this particular case, it's equal to weight of the body, but it could be different. For instance, on some inclined plane, we will, as we considered previously. And it doesn't have area of two surfaces in contact with each other, which is a bit counterintuitive, but that's what it is. Area of this contact surface does not define the static friction. As well as dynamic friction, like this kinetic friction, which is called, which we consider right now. So obviously, if applied force is larger than the static maximum value, static friction force, this body starts to move, and then another type of friction force appears, and that is kinetic friction force, which also is aligned in opposite direction to the driving force F, applied force, and can be given its magnitude as mu k times n. So here is kinetic friction coefficient, which is usually a bit smaller than the static friction coefficient. That's why if we now try to show graphically friction force versus applied force, so we will see something like this. It will increase proportionally. While we increase applied force, static friction force will increase, so it will be equal to the applied force, but until some maximum point, which is defined by mu s times n. Then we get very abrupt decrease, slight decrease of this friction force, which happens in the moment when a body starts to slide over this surface, and it saturates at the level defined by kinetic friction force. So we can divide these two in two regions. It will be static and kinetic. Okay. Now we need to introduce another force, which is important, also friction related force, but it's called drag force. So imagine that you have some ball which is moving in water or in air. Some environment which is in contact with whole surface of this ball, and it has some velocity v, and of course it interacts somehow with this environment around, let's say with air. That creates some force which slows down this body, and that is called drag force. So drag force for low speeds is proportional to velocity. So drag force is equal to minus kv Minus means that drag force is always aligned in opposite direction to the velocity vector, F drag. So here is the key difference between drag and kinetic friction forces. Kinetic friction force is independent on velocity. It doesn't change with velocity. However, drag force depends on velocity. Moreover, when this velocity increases at some point, it becomes even stronger dependence. So drag force at high velocity is defined as minus K1. So this proportionality coefficient, which defines the surface of the body, like conditions, rough, smooth, shape of the body, and also properties of the environment where it moves. It can be air and water. Obviously, it's much more difficult to move underwater than in air. And here will be V squared. So it will exhibit even higher dependence on velocity. So there is some terminal velocity, which is maximum velocity at which body can move at given conditions in the gaseous or liquid environment. So, for instance, let's say we have some body which is falling down in air. Here is mg, and here is F drag. At some point, mg will be equal to minus k. Well, here we don't need to put this minus, it's just projections, equal to k1v squared. And this v will be terminal velocity. So we can calculate it. V terminal is equal to mg divided by k1, and this is square root of it. So for free falling, there is constant force which acts on the body, means its weight, and it will accelerate while falling down. However, the drag force will increase, and it will compensate the weight at some point because we have this dependence of drag force on velocity. And the maximum velocity at this or maximum speed, which can be reached under this falling of the body in given environment, is called terminal velocity or terminal speed. Another thing which I wanted to highlight, that keep in mind when we apply laws of motion to drag force, that's not so straightforward as with kinetic friction force, because again, on this dependence on velocity for drag force. The thing is that if you consider, for instance, some body, like let's say ball, we provide some initial velocity, v naught, it moves in air, and at some, let's say it's v naught is at time t equals 0. And then it moves in air, and because of drag force, it slows down. So you could write the second law of motion. It would be ma, which is acceleration, like of slowing down the ball in air, is equal to minus kv. Actually, no, again, we don't need this minus here. Is divided by Yeah, so this MA is equal to KB, which is defined by the drag force. And we cannot get exactly this acceleration because the drag force depends on V. And then we need to deal with some differential equation. So we need to express A as the first derivative of V. So it's m times dV over dt and equal to kV, because at each given moment, as opposite to kinetic friction, which is constant, drag force will change while the ball slows down. So in this case, and this will be negative because we reduce velocity with over time, so it slows down. Derivative will be negative. And now we can rearrange this. Will be minus m over k dv divided by v is equal dt. And then we can integrate left and right side. So here we'll not go into details, but the most important to understand this concept that drag velocity depends on v. V is a function of time, means drag force is also is function of time. So from this differential equation, we can get how V depends on time. And then from here, we can get drag force as a function of time because it's equal to K times V as a function of time. So this should be taken into account, and such cases should be approached with this like differential equation. For this particular case, it's quite simple differential equation. You can just split variables into left and right side and integrate them. So it's quite straightforward. But the most important to understand this difference between drag force and kinetic friction force, which is constant. Okay, so let us consider some examples with this friction, and then we will move to circular motion. So again, as I mentioned at the beginning, let's consider inclined plane. We have some weight, mg of this body. We have reaction, and we have some component of this mg along the inclined plane. Will be m, here it will be angle theta, will be mg times sinus theta. This is component of mg in the perpendicular direction, which will define n, and this is mg times cosinus theta. And here we will have some fs. Will be our static friction. So the question is, at which angle theta this body will start to slide on the inclined plane. So if so we know that Fs is equal to mu s times n. So this will happen this moment when the body starts to slide down, when this like driving force along the inclined plane will be equal or larger than Fs. So we can write that mg times sinus theta is equal to mu s times n. And instead of n, we can substitute this expression. It will be mu s times mg times cosinus theta. So mg can be cancelled out. And from here, we already see that sinus theta over cosinus theta, which is equal to tangent theta, is equal to mu s. So only this static friction coefficient will define the angle theta at which this body will start to slide. So interestingly, that the mass of the body doesn't make and doesn't influence on this value of angle theta. Only friction coefficient, static friction coefficient. Okay, so now let us go for maybe a few examples with uniform circular motion and application of laws of motion in these cases. So let's go to another slide. First, let us consider some body attached to a massless and not stretchable rope. And then we have some rotation of this body attached to this rope about an axis, which goes through the point where this rope is attached here. So what forces are acting on this? So it rotates with some angular velocity omega. So what forces will
Centripetal.
Sure. Yeah, but so let's start from mg, the weight, obviously. Then always, of course, we will have this centrifugal acceleration, and force which we need to consider should be centrifugal force acting here, will be equal from our previous discussions as m times omega squared times r, where r is this radius of the circular trajectory. So few words on this centripetal and centrifugal acceleration forces. So obviously we have this centripetal acceleration, which is pointed towards the center of the circular trajectory, and that will be, yeah, you are right. So it's how centripetal acceleration is defined with linear velocity, but can also be defined with angular velocity, which we are doing right here. But now matters orientation. So it's pointed out to the center, and obviously there is some centripetal force. And if we consider some body attached to a rope and we start to rotate this rope, and as external observers, we see that there is some tension in the rope, which keeps this body moving on circular trajectory. So that is centripetal force, and it's like real force. However, there is also centrifugal force, and that is it's called apparent force. So if you are part of the rotating system, then you experience that there is some force pushing you away from the center of this circular trajectory. And it's kind of reaction force towards the centripetal force, which keeps you on this trajectory and pointed out towards the center of the trajectory. So technically, these are the same forces. However, it's kind of like different sides of the same coin. It's just the matter of frame of reference. If you are observing rotate a circular motion from outside, you kind of deal with centripetal force pointed into the center of the circular trajectory, because there should be some force which keeps the body moving on the circular trajectory. Otherwise, it would just go on a straight line, and that's all. However, when you are technically part of the system and like your body of the consideration, you definitely experience force which the centrifugal force which pushes you away from the center. So if you go to some attractions where you're spinning with quite high angular velocity, you will feel quite a huge force on your body which wants to push you away from the center. And that is why, because you are part of this rotating system, and from your perception, you experience this apparent centrifugal force. So that is just some comment on this centrifugal and centripetal forces. So because quite often it's not, it's a bit confusing and people can mess it up. So now let us maybe down here show just the force diagram, so it will be not so crowded and we can see better which forces. And also we forgot here to put will be tension in this row because we need to compensate these two forces. Otherwise, it will not be in this stationary condition. So here will be angle theta between the rope and this axis of rotation. So what we would like to figure out now, which parameters will define this angle theta. So for instance, if we want to increase this angle theta, which parameters we need to increase? Or which?
Velocity.
Yes. Do you have a question? Yeah.
I mean, we should increase velocity.
Sure, yeah, but not only. And again, how much? Because it may depend on different parameters in different degrees. For instance, it could be some linear dependence, could be some exponential dependence. We want to figure this out. So let's say we have, again, just forces here. It's mg. Then we have this centrifugal force, m omega square r, and this tension force. So this angle here will be also theta. And we need, in order to have this stationary condition, we need to compensate both projections of this tension T on, let's say, X and Y axis with respective weight and centrifugal force. So we can write for axis Y that mg should be equal to T times cosinus theta. So this T times cosinus theta is this part. So it should be compensated by the weight of the body. And then for the other direction, it's this part of our tension vector. And this will be m omega square r is equal to t times sinus theta. Okay, now we have this condition of equilibrium. So we can express t from the first equation. T is equal to mg divided by cosinus theta. And also what we need, so we have here r, but what is given is L, the length of the rod. So in order to get r, we can express it with this length of the rope and angle theta. So it will be L times sinus theta. So now we can substitute R here and T here. So let us do it. It will be M omega square times, times L times sinus theta. And this is equal to mg divided by cosinus theta times sinus theta. Okay, so m and m cancels out, which means that mass will not already have an impact on theta. What is interesting and maybe not so clear from first point of view would consider, okay, maybe heavier object would result in smaller theta, but you see that we cancel it out. And then we have sinus theta. So we can express now cosinus theta will be equal to G divided by omega square L. So what do we see here? If we increase G, acceleration of free fall, then cosinus theta will increase, means theta will decrease. So stronger gravitational field will result in smaller theta. Then for omega and for L, if we increase them, cosinus theta will decrease and theta will increase. And that is how we get specifically, you mentioned about velocity. So angular velocity, you see it goes in second power. So angle will linear, like it's 1 over L dependence, will decrease with the theta will decrease with the increase of length of the rope, but it will exhibit way stronger dependence of this theta will exhibit much stronger dependence on angular velocity because we have this in second power. So this we considered, and maybe let us consider one more case. We have a few minutes left. Let's consider some curved road and some car moving on this road. So there is some velocity vector, and here is the radius of this curvature. The static friction coefficient between tires and road is mu(s). And we want to understand what will be the maximum velocity of this car, at which, like maximum speed, at which it will start to slide on the surface of the road in perpendicular direction. So it kind of will be sliding away from the road, which is, of course, very dangerous condition, and you should not come to such driving experience. So let us consider this from the cross section. So here is our car, some wheels and tires are in contact with the surface. This is horizontal surface. Here we have mg. Here we have n. Again, here in this direction, we have centrifugal force, which is mv squared divided by r. And here we have static force, friction force. So obviously, in order to start sliding, this mv squared over r should be equal or larger than static friction force. And this is equal to mu s times n. So from here, so here we can call it maximum, V maximum. And n, again, we can express as mu s times mg. So here m and m can be cancelled out. And we can get the expression for the maximum velocity, V maximum square over r is equal to mu s times g. From here, V maximum is equal to square root of mu s times g times r. So we see that if we increase radius, so becomes less curved road, then we also can increase maximum velocity. So cannot go very fast in strongly curved roads because there is a chance that you will be just slide away from the surface. G matters, and of course the friction. So it's a big difference if you go into this curved trajectory of the road when you drive during summer, when the asphalt surface is under normal conditions, or during winter when it's covered with snow and ice. Definitely this mu s will be smaller and maximum velocity allowed will be much lower. That's why it's important to replace your tires from summer to winter, and don't forget about this. It's your safety. That improves much more. This increases mu s, and obviously then this maximum critical velocity is higher, so you can safer drive and with less chances to be slide off the road. Okay, guys, so these are different examples of second law of motion, like laws of motion application. Yeah, you have a question? You're welcome.
Yes, I have a question regarding the long kappa.
Okay.
Like when we are entering the numbers, should we like round them to, for example, 3 significant numbers, or how should we enter them?
Yeah, 3
For example, let's
numbers, that's sufficient.
Okay. So exactly 3 significant figures, right? Okay.
Yeah. I think it should be always the optimal choice to go. So usually it just tells that there is not enough significant numbers, like significant figures. But if you put like 3, that is accepted. It could automatically then reduce and say it's like, for instance, correct answer, and show you answer with less significant figures, which is a bit rounded already. But if you put this all significant figures, like 3 significant figures, it will be accepted. And I think it's better to go like this.
I'm sorry. How about like, will it be counted right if I enter all the numbers like without rounding?
That's okay. It will be
Okay.
this number without rounding is correct, is within, you didn't make any mistake, and it's within plus minus 1%, then yeah, it should be accepted. Yeah, I see that there are some questions about v squared divided by r. Well, we derived this quite in detail. So if we check our previous discussions, there was some phenomenological derivation when we considered just some geometry features, and also we derived it with calculus. We got in terms of angular velocity, omega squared times r. So we did it definitely at the beginning. So when we considered two-dimensional motion and circular motion, so you can check this out, why these equations are like this and not other. Yeah, sure. There's a question about this answers with 4 significant digits. It will accept it. If it doesn't have enough significant digits, then it will complain, but more, that's okay. It just has to be correct. Okay, you're welcome. Good. Thank you very much for attention. I wish you good weekend. And yeah, don't forget to finish your homework assignment and submit it in time if you haven't yet done that. And take care, be healthy, and see you on Monday. Bye-bye.
See you.
Goodbye.
Bye-bye.
Mhm.
Goodbye.
Bye.
Goodbye.
Goodbye.